Okay, so now let's get into our notes and fill in some of the notes about the demonstrations that you just saw regarding strong electrolytes and weak electrolytes. And I really didn't do one with non-electrolytes. I could have done pure water, and I didn't really think about that while I was at school. I'm on page 16 of your guided notes. So if you want to get to that page, that would be great. You can always push the pause button, remember, as you're trying to get things organized. So then once you're ready, you can go ahead and get back on and be ready for that. So when we think about strong electrolytes, and you just saw this with the demonstration, we are looking at those things that dissociate completely. So they have the ability to conduct electricity because they form lots of ions in solution, and they completely dissociate, kind of like what we talked about. So strong acids and bases are strong electrolytes, and so are most salts. Now, we're going to be reminded of how to determine if a salt is soluble or not. So we'll go back to the unit whenever we learned about chemical reactions and how to use the solubility chart. We're going to see that again. Weak electrolytes, these are going to conduct electricity only weakly, so partially, just like what we saw at the demo, because they form only and we're going to write more than just this, form only a small amount of ions in solution, and they partially dissociate. So weak acids and bases would be considered weak electrolytes. Non-electrolytes, so these will be things that just will not conduct because they don't make ions. Covalent compounds, so any compound, pure water would be like this. Anything that is covalent, ethanol, methanol, hexanes. So it maybe can dissolve in a water compound, but it just is not going to dissociate. It's not going to be able to be an electrolyte. So that's an example. And we should probably add in here insoluble salts. Okay, in case I throw something like that at you. And you might even want to consider there are what we would say, ooh, I messed up on my words, you guys. Oh my goodness, we're starting over on that one. Insoluble bases. There are a few bases out there that will not dissolve in water, or they just barely dissolve. So that's something we've got to be a little careful about, are those insoluble bases as well. Okay, so then if you go ahead and flip the paper over, we have some practice that we can do. We're going to fill in this table together. You're going to want to have this is on page 16, but then also get your reference sheet out. So I think your guys' is, if you're in my class, it's purple. I don't know what color Mrs. Merkis's is, but we're looking at this sheet, and we're going to pay attention. We're going to go back to the solubility chart that's on here. And then I kind of glossed over it in your notes because on your reference sheet, we put off on the last page, on page 4 of your reference sheet, we have this table of what are strong acids and strong bases. And remember what I said, if it's a strong acid or a strong base, it's a strong electrolyte. Anything else that's still an acid or a base, but not on these lists, are weak acids or weak bases, and they're going to be weak electrolytes. And then we got to think again, covalent compounds are going to be non-electrolytes, and then insoluble salts would be non-electrolytes. So we're going to use this reference sheet to kind of help us fill out this table. So if we look at this very first one, HCl, you know, I'm hoping being able to identify at this point that it is an acid, but here's where I've got to go off my reference sheet because it's going to help me fill out the rest of this. So looking on this sheet, I would see that HCl is a strong acid. It's right here. So it being a strong acid, and I might even write that to kind of remind myself, okay, that's strong. Is it going to break apart in water? Will it dissociate? And the answer is yes. Okay, is it a strong electrolyte, a weak, or a non? Now remember, strong acids, strong bases, they're strong electrolytes. So that would be like the hydrochloric that I did the demo with the light bulb, or sodium hydroxide would work with this too. Okay, So KBr. So when I look at this next one, I have to recognize that it's not an acid, it is not a base, this is actually a salt. Okay, so a cation and an anion. I don't see hydrogen in here, there's no hydroxide in here, so this is a salt. But I probably want to do a step further and remind myself with whether it's soluble or not, because if it's not soluble, it's not going to break apart in water. So I'm going to go back to my reference sheet, and we have not used the solubility chart in quite a while, so kind of get yourself oriented with it. And we're looking at KBr, potassium bromide. So we want to first go down this side. We want to find our bromide that's right here. We go across. If it was one of these top ones that was bonded with bromine, then it would not be soluble, but it's potassium. So I don't see potassium on this list. So potassium would be that any other cation group. So potassium with bromine, well, that tells us that it is soluble. So potassium bromide is soluble. And I just might write that off to the side to remind myself. So yeah, that means it's going to break apart, just like how sodium chloride does to make saline solution. If it is a soluble salt, remember that was our third type of chemical that can be a strong electrolyte. And I suppose I could have shown that as well. You have all these thoughts after you leave school, I suppose. I could have just put sodium chloride in a beaker of water and shown how it would conduct electricity. I think I did this back when we were talking about bonding, and I did some demos like that to show you that salt water would conduct, but something like sugar would not conduct because it's not an ionic compound. Okay, let's look at this next one. So we have sodium hydroxide. My clue to know that it's a base, ammonia is the only weird one out there that we're going to hold you accountable to know that it's a base. Ammonia doesn't have a hydroxide ion in it, but it can form one when it reacts with water, and that's what makes it a base. Everything else that we give you is going to have a hydroxide in there. So whenever we look at this, I know it's a base because it is a metal. It's a cation that's attached to a hydroxide. This next one's going to be a little tricky. Okay, this one's not a base. We'll think about that in a second. But here we have an ionic compound, a cation attached to a hydroxide, and there's that hydroxide right there. So this is a base. But let's take it a step further and actually categorize what type of base it is. So I'm looking on my reference sheet, and I can see right here, sodium hydroxide is listed as a strong base. So because it's listed as a strong base, just to help me, it didn't ask me to do this, but give me a little bit more direction, we're going to write that it's strong. Will it dissociate? Absolutely. Even weak ones would dissociate, so let's write that it would. And then, is it going to be a strong electrolyte, a weak electrolyte, or a non? Well, because it's a strong base, it's going to be a strong electrolyte. Okay? Now, I told you, be careful with this next one. Because the truth is, you might go, oh, there's an OH, it must be a base. But it's not, because to be a base, it has to be a metal with a poly, so a metal with a hydroxide ion. These are all non-metals. So this is actually a covalent compound, which would fit under this category of an organic. So I'm going to write covalent, but really it's also organic. Now remember, if it's a covalent compound, we just wrote in our notes before, it doesn't have the ability to break apart. It doesn't even want to break apart. Okay, it can polarize water. It can be polar or nonpolar, but it's still not going to conduct electricity. So is it going to dissociate? No. What do they mean by dissociate? Like if we go back to this, dissociate would be that it literally is going to split. When we put it in water, these are going to split into their ions. There's no ions for it to split into here. So this will not dissociate. Because it doesn't dissociate, it is a non-electrolyte. Okay, for your sake, I want us to add 2 more rows here. So give yourself a moment to just do that. And I'd like to do 2 more examples that weren't originally in here. So take a moment to do that. And one of those examples goes to one of the chemicals that we actually, this is a tough one. Okay, so one of the chemicals that we actually played around with in the demo. So this is CH3COOH. Now, I might write it a little bit funny, but if we think back to nomenclature and our polyatomic ions, I don't have that sheet in front of me, but on our periodic table, we would see from here to here, that's actually the acetate ion. Remember that this is the only positive polyatomic ion. So we do have ions here. So here's our acetate ion. Here is our hydrogen. Okay, so acetate, hydrogen. We have ions here. Because of that, and because this hydrogen is our lonely ion, sorry, I don't know why I said our only positive polyatomic. Acetate is not, it's negative. I don't know why I said that. Sorry, you guys. So CH3COO is our negative ion. Hydrogen is our positive ion. So this is the vinegar example that I did. This is an acid, but when I look on my sheet to figure out if it's weak or strong, it's not a strong acid. It's not here. I don't see CH3COOH anywhere. Sometimes it's abbreviated as like C2H3O2 and then an H that follows, but that's not on here at all. So therefore it must be weak. Remember, if it's not on that list, it's weak. Weak acids, just like you saw in the demo, will still break apart. They still have the ability to break apart. They're just not going to do it as well. So will it dissociate? Absolutely. We saw that tiny little light bulb light up on that special little meter. Oh, why did I write no? So it will still break apart. But it doesn't do it as well as that hydrochloric acid did or the sodium hydroxide acid did. So then we get to classify it as a weak electrolyte. Okay. All right. The last one I wanted to do is lead sulfate. So it's really lead 2 sulfate, so PbSO4. And we take a look at this, and again, I see no hydrogen ions. I see nothing that's a hydroxide. It's not ammonia, so it's not that special base. I should be able to catch that there definitely are ions in here. I've got my lead ion, I have my sulfate ion. So I know that it's not covalent. So I do know it's some type of salt. Remember, a chemist calls any positive, negative ion combined together to form a compound a salt, not just sodium chloride. So now we got to find out if this salt is soluble. So let's go back to our reference sheet, and we're looking at lead sulfate. It's organized by our negative ions, so I find sulfate. I come over here, and my lead, my Pb is up here. So PbSO4 is what I was interested in, and look here, it says that it's insoluble, very low solubility. So we're going to assume that it's insoluble. So therefore, we go back to this, and we want to write insoluble. Now, if it's insoluble, who cares if it's in water or not? This would be our precipitants that form, that fall out of solution. So they're not going to have a chance to dissociate. So does it dissociate in water? The answer is no. Therefore, because it doesn't dissociate, it's a non-electrolyte. Okay, so we are going to stop here for today. On Monday, Mrs. Marcus is going to walk you through how to write net ionic equations and what that means. It deals with these strong and weak electrolytes. Pay attention to the tasks. It's going to tell you which problems to attempt in the acid-base packet that you should have. And the answers are also going to be posted in there. So take a look at all of those things. Hope you're doing well. Take care. Bye-bye.